Okay, so last section we'll look at this week is 10.2. In 10.2, it's going to be doing the same kind of thing we've done before, solving a system, except now we're going to learn how to do it with a matrix. Even doing it with a matrix, there's multiple ways to do it. The specific way we're going to use a matrix to do it is called Gauss-Jordan, or actually Gauss elimination. It's like half of Gauss-Jordan. So I'll explain what it is. I'll explain the difference between the two things I just said. And if we have time, we could do a full Gauss-Jordan elimination. But it's just different ways to solve systems. So basically the goal is you're going to look at the first equation. And we're going to try to use the first equation to eliminate variables in the other equations. Okay, so it's kind of like we're going to be working from the top row down. And I think I'm going to hold off. You can copy this down, but I'm going to hold off on actually doing it this way. I think I'm just going to do it with a matrix. But those are the steps to do it, and we'll come back to actually doing it once I show you what a matrix is. Okay, but the process in general would be use this value to get rid of x here and here. So if you wanted to get rid of x in the second row, and you wanted to use the first row to do it, what would you have to multiply the first row by so that when you add it to the second row, you get 0 for the x's? -2. So the first step here would be to take row 1, multiply it by -2, and add it to row 2. And row 2 would change. Okay? It would change, and there would no longer be an x in this first spot. It would be a 0. And then what if you wanted to get rid of x in the third row using the first row? How would you do that? Times what row? Remember, you're always using the what row? The top row. You're going to use the first equation to eliminate x in the other ones. So multiply this one by -1, and then add it to row 3. And if you did that, the x's would be gone. You'd have a different y value, a different z value, and a different constant as well. But the goal would be just to get rid of the x's. Okay, so the order that generally you're going to do things, you're going to deal with that one, then you're going to deal with that one, okay, then you're going to deal with that one. Okay, that's kind of the order. Right? And I'll explain a little more as we go through it. The idea is you start with the top row and you have to work your way down, working in the first column first, and then the second column after that. If you don't follow the right order, okay, what'll happen is you may wipe something out here, which is what you want to do, get a 0, but you could undo it if you go in the wrong order. You could mess something up, and then all of a sudden you end up with a number back here. Okay? We don't want to do that. Once we turn something into a 0, we want it to stay a 0 forever, for the rest of the problem. All right, so we're going to use a matrix, okay, to represent our equations. So the way we describe a matrix is with its dimensions. So in my example, I use the letters m by n. So if you had an m by n matrix, m is the rows, n is the columns. And it's important to know the dimensions because when you get into doing certain operations with matrices, you can only do them if the dimensions are right. Like if you told me to just take any matrix and multiply by any other matrix, I might not be able to do that. They have to, the dimensions have to be correct for that to happen. And that's something a little different than with numbers, because if you just said take this number and multiply by that number, I can multiply any 2 numbers I want, but not any 2 matrices. They kind of have to be compatible, you could think of it that way, to multiply together. But for what we study, we don't really get into multiplying matrices. Okay? But it's still important to kind of understand how you describe a matrix. If the number of rows and columns are the same, that's called a square matrix. And we're going to be working with a lot of square matrices, most of our problems. Okay, the individual numbers in a matrix are called the elements of the matrix. Okay, so here's a 3 by 3 matrix. It's a square matrix. And I've labeled this matrix A. Okay, a lot of times they name a matrix with a capital English letter. Bless you. And then the notation, if you wanted to describe a specific spot in that matrix, I've shown on the right. Okay, if you want to describe to me the element or the number in row 2, column 3, that's how you would reference it. They use a lowercase letter, which corresponds to the name of the matrix, and then a subscript 2, 3. So that means in matrix A, row 2, column 3. So row 2, column 3, there's your 9. We don't really reference elements in a matrix a lot. We don't usually have to write that down. But that's something very, very basic you do with a matrix. Just identify where something is. Okay, so any questions on those terms? Square matrix, elements, rows, columns, dimensions, all that stuff. Okay, and if you do any kind of work, like on a computer, if you do programming where you're designing like things that are visual, so like game design or anything like that, matrices are used a lot, okay, for all kinds of stuff. They're really important, combined with like sine and cosine. When you take matrices and instead of just putting numbers in here, you start putting sines and cosines in here, now you can take objects in 3D and start to rotate them or move them. So if you were designing something in a game, you might want an object to be rotating, and you can make it rotate using a matrix. So they're used a lot if you do any kind of visual artwork on a computer. If you use like Photoshop or something like that, that's different. That's not, all this kind of stuff happens in the background. You don't need to understand it. But when you're doing like the actual programming of a video game, this is how they do a lot of animation and stuff like that.
How come the one letter's capital and one's lowercase?
That's just the kind of the notation that they use. I don't know if that's definitely how our book does it. I'm not sure if every single book does it that way, but for our book, the purpose of doing that is to distinguish an element in a matrix from the name of the matrix.
So that's matrix A?
Yep. So when you see a capital in our book, it's referring to the name of a matrix. When you see a lowercase letter, it's referring to an element in the matrix. Okay, so the big advantage of a matrix is that you only need to write the letters. You don't need to write the letters. You're only going to write numbers in a matrix. Okay, so it's going to save on a little bit of writing. When you write things in a matrix, each column has to represent the same letter. So in this matrix, these might be your x's, your middle column is your y's, and your last column is your z's. So this first row might represent 2x plus 4y plus 6z. Okay, and then x plus 5y plus 9z, negative 8x plus 3y. That's the last row. That matrix, okay, that you have, that's going to be a square matrix because we're going to have 3 equations. We're going to have 3 variables. So that's 1 row for each equation, 1 row for each variable. That's called the coefficient matrix. Okay, so if you were to put, just go back to this one, everything in that box in a matrix, that would be the coefficient matrix. 1, negative 2, 1, 2, 3, negative 2, 1, 3, negative 2 for this problem. Now, we're going to add something to that coefficient matrix. Okay, because if you look back at the problem I I put a box around. I left this off, okay, those three numbers. Those three numbers are very important, though. They're part of the equation. So what we're going to do is we're going to add one extra column onto the coefficient matrix. And that column is going to represent the constants that were on the other side of the equal sign. What I'll usually do is separate it with a vertical line. So if this is my coefficient matrix, I'll put a vertical line like that. And the three numbers that I put right here will represent the constants that are on the other side. Okay. Also, a lot of times we put brackets around it. I'm probably not going to put brackets around it all the time just because it's more writing. Okay. But understand when you write a matrix properly, it always has brackets around it. Okay, so any questions on that column that we're going to add onto the coefficient matrix? All right. So now that we've set this up, there's a lot of different ways you can use it. Okay, the way we're going to use it is this method. Okay, the goal is to get our matrix in what we call row echelon form, okay, which I'll abbreviate REF from now on. Okay, all that row echelon form means is that on the main diagonal, which goes upper left to lower right, you have all ones for coefficients. And below that, you have all zeros in every spot. Okay, so row echelon form, you've got a matrix with 1 on the main diagonal, zeros below it. Now, if we wanted to take that one step further, we can do what's called reduced row echelon form, which means 1's on the main diagonal, zeros below, and zeros above. If you do that, then the whole problem is done using what we call matrix operations. If you only do row echelon form, it's like you're only doing half of it. And you're going to have to go back and use substitution to finish the problem. Okay, so the two options are do row echelon form and finish the problem with substitution, or do reduced row echelon form and do the whole thing with a matrix. Don't use any substitution at all.
What is the line about the ones?
This, just anything.
Oh.
Could be anything. If you're doing row echelon form, those would just be random numbers. Okay, but that's the goal. At a minimum, 1's on the main diagonal, zeros below. And the only way you can do things to a matrix to get it in row echelon form is to use operations, okay? Basic operations that you're allowed to do. These operations do not affect the answer. Okay? Because if you did something that affected the answer, that wouldn't be good. Now, these operations affect other things that we are not talking about. So we don't have to worry about them for our purposes. But I'm just letting you know that what we're about to do, if you were looking for more than just the answer, and there is other stuff you could look for, these operations might mess up some of that other stuff. Okay, but they're not going to mess up what we're looking for. Okay. One thing you're allowed to do in a matrix is swap 2 rows. Okay, you can take any 2 rows and swap them. You can take a row and you can multiply it by a number that's not 0. Generally, we try to multiply by numbers that aren't even fractions. Okay, you can, if you have to, but just keep in mind things are going to get messy if we start using fractions. Okay, so we try to avoid fractions as long as we can, and if we need to, eventually we'll use them. And the third thing you're allowed to do is add a linear combination of one row to another. Okay, so the third one, that one we use a lot. Okay, so an example of the third one would be something like take row 1, double it, and then add it to row 2. That's adding a linear combination of one row to another row. But those are the only 3 things that you are allowed to do that will not mess up what we're looking for. Hey, any questions on that?
When you do the third one, do you still keep row 1 the same after?
No, oh yes, row 1 will stay the same. Yeah, if you do the third one.
Okay.
And you'll see, we'll do that. There's a lot of stuff we do in our head here that we don't write down on paper. So there's a lot of, it's basically a lot of multiplying and then adding, multiplying and adding, multiplying and adding a lot. Okay, so we just have to be careful when we do it. Okay, and this whole process is called Gaussian elimination. Okay, so you might see that term on the test. If you see a problem that says solve using Gaussian elimination, that's the process of turning a matrix into row echelon form using these 3 steps. Okay, so I can write that down. So process of getting a matrix in row echelon form using the elementary row operations I mentioned above. Now, if you took it one step further and you got the matrix into reduced row echelon form, that would be called Gauss-Jordan elimination. Okay, Gauss-Jordan elimination is doing the whole thing with the matrix. We're going to have to go back and still do substitution if this is all we do. So maybe we'll try one with substitution, and then we could try a full reduced row echelon form if we have time. I don't know if we will. Okay, so this is the very first problem that I said we're not going to do it 2 different ways. I could have done it the way we learned yesterday and then done it with a matrix to show you get the same answer, but we're just going to do it with a matrix. So the first step is to make a matrix. You've got to put all those numbers in a matrix. Okay, so what would be my first row in the matrix? 1, -2, 1. Okay. Yeah, we'll just put a line that'll separate the number that's on the other side. -1. Next row. 3, and third row. 3, -2, -2. So we can't forget about this last column. If you, whatever you do to the first part, the coefficient matrix, you got to do to this part too. Okay, you got to treat everything the same. All right, so the goal is to always start with a 1 in this position. Do we already have a 1 in the upper left? Yes. If we didn't, there's a couple different ways I could get a 1 there. If I had another row that had a 1 in it, I could swap it with that one. If I didn't have any rows with 1s, for a second, let me just make up something, a smaller matrix. Let's say I had to do this problem. Well, swapping rows isn't going to get me a 1 in the upper left. You're not allowed to swap columns. You can't do that. So what I could do is multiply everything in row 1 by 1/2. That's one way I could get a 1 right there. The only disadvantage is that's going to give me a fraction here. 3/3/2. That's not an awful fraction to work with. Okay, but that would be one way to get a 1 in this spot. Any questions on that? Okay, so not something we need to worry about on this problem. So the next step is to get a 0 here and here. And you have to do it in that order. Get a 0 in the first column, second row, and then first column, third row. All right, so I'm going to put an arrow, and above this arrow, I'm going to write down how I'm going to do that. So using the first row, what would I have to multiply it by and add it to the second row? -2. So what we're going to do is we're going to say row 1, and anytime you write a number and circle it, that's going to represent a row. So we're going to do row 1 times -2. You could put it after it, but it's easier if you put it before it. So we're going to do -2 times the first row. We're going to add it to the second row. And we're going to put the answer back in the second row. So this was the question Dave was asking. What's going to change? Row 2 is going to change. We're going to do this calculation. And think of this arrow as like the word store. You're going to store the answer in row 2. All right. So we could also do row 3 at the same time. But let's start with row 2. So row 1 is going to stay exactly the same. Okay. We're not replacing anything in row 1. All right, so row 1 doesn't change. We're not storing anything in row 1. Now, let's fix row 2. We're going to do -2 times the first row, added to the second. Okay, so I'll say each calculation and just kind of ask you what to write. Okay. What's -2 times 1? Plus what's here is 2. What's -2 plus 2? 0. Okay. What's -2 times -2? 4. Plus what's here? 7. Okay. What's -2 times that 1? -2 plus what's here? -4. What's -2 times -1? 2 plus what's here? -1. Right. So that's this operation that we just wrote. That's what we did right there. Now, do people want me to do another operation in the same step or write it as a different step? Same step. All right, so right above this, I'll write another calculation. Or I could write it below it. Doesn't matter. What would we have to multiply row 1 by and then add it to row 3 so we could cancel the x's? Yes, you'd have to multiply this by -1. So we're going to do -1 times the first row. We're going to add it to the third row. And where am I going to put that answer? In the third row. Okay, so now let's do that. If you didn't want to do that here, you could just copy row 3 the way it does and write this as a whole new step. But then you're going to have to copy things a lot. All right, so -1 times the first row. What's 1 times -1? Plus 1. 0. -2 times -1? Plus 3. 5. I lost my spot. -2, whoops, I'm sorry, 1 times -1 minus 2. -3. And then -1 times -1 minus 2. -1. Okay, so it's very easy to make a mistake, and unfortunately, if you make a mistake, it messes everything up after that. So if you notice anything, let me know. Okay, any questions on that? Now, you can no longer use row 1 to do anything. Because if you use row 1 to affect something, you're going to mess up these zeros. So the only rows you can work with now are 2 and 3. Okay, we have to forget about row 1. Okay, questions on that? Okay, so now the next step is you want to have a 1 here. Okay, do we have a 1 there? No, we have a 7. So one way you could get a 1 there is to divide or multiply everything by 1/7. All right, and then we're going to get a lot of fractions. But if I can get this number closer to 1, like if I can get it to be a 2, I don't mind multiplying things by a half, because a half isn't as bad of a fraction to work with. So does anybody see something? I mean, again, you could do the 1/7 and go from there. But does anybody see something we could do with row 3 to multiply that by and add it to row 2 to try to get this number closer to a 1? Yeah?
You're going to multiply the third row by a -1, so when you add it to the second row, it will become a 2.
Yeah, it'll become a 2. All right? And honestly, I'd rather work with this as a 2 than a 7. So I think that's what I'm going to do with this step. I'm going to take the third row, multiply it by -1, add it to the second row, and I'm going to replace what's in the second row so I have something a little closer to 1. It won't be 1. If you could get it to be 1, that'd be ideal. But in this case, we can't. So top row is going to stay the same for this entire problem. It's never going to change again. 1, -2, 1, -1. Third row in this step is staying the same. 0, 5, -3, -1. Okay, second row. We're going to take -1 times the third row and add it to the second. What's -1 times 0? Plus 0. It's okay to work with rows 2 and 3 because you'll never mess up those zeros again. Just don't work with row 1 anymore. Okay, that one's done. What's 5 times -1? Plus 7? 2. That's better. Now, what's -3 times -1? And what's 3 minus 4? -1. And lastly, multiply -1 times -1. And then -1. 0. Okay. Any questions what I did there? And now you can keep playing this game to try to get a 1. I'm going to multiply everything by a half now in row 2. Another thing you could do is you could take this second row now, multiply it by -2. That would give you a -4. And what's -4 plus 5? A 1. And then you could swap the rows. So if you didn't want to multiply everything by a half, you could keep playing this game until you finally get a 1 somewhere in one of these spots. And then you could swap the rows if the 1 is in the wrong spot. Okay? But I think it's going to be easier. Let's just multiply by a half at this point. Okay? So I'm going to take 1/2 of row 2, and that's going to replace what's in row 2 right now. So I'm not changing 1, and I'm not changing 3. 1, -2, 1, -1. 0, 5, -3, -1. And what do I get if I take half of everything in row 2? 0, yep. 1, -1/2, and 0. Not bad. It's only one fraction. Okay, so we've got zeros in the first column. We got a 1 in the second. The next thing I want to do is get a 0 here. And that's why I made this a 1. Because it's very, very, very easy to get a 0 here if this is a 1. You just have to multiply it by what? -5. So we're going to take -5 times what row? Second row. And we're going to add that to what row? The third. And that's going to replace what's in row 3. And after this step, we're like 80% done the problem. Even though we don't even have any answers yet, we've already done most of the work to get all the answers. And they're going to come very, very quickly after this step. So, keep top row the same. Keep the second row the same. And now the third row. Well, if I do -5 times anything that's above it and add it to what's below it, I'm still going to get 0. What's 1 times -5? Plus 5? 0. What's -1/2 times -5? It might be easier to think of it as a decimal. 2.5. And what's 2.5 take away 3? -0.5 or -1/2. For me, it just helps to think of it as a decimal to do it in my head. And then 0 times -5? -1. -1. Now my last step is to get a 1 right here. And then I'm going to be able to get all my answers very quickly. So how could I get a 1 in the spot that I just circled? Multiplied by what? Yeah, take negative 2 times the third row and replace what's in the third row right now. And this is going to be our last matrix step. We're going to be done with the matrix now. Top row, keep it the same. Second row, keep it the same. Third row, multiply everything by negative 2. So what's the first number going to be?
0.
Second number? Third number?
1.
Last number? 2. Now, that's enough information to now solve our problem, and we should already know one of the letters. What does this last row say if you changed it back to an equation? Z equals 2. Right? It says 0x plus 0y plus 1z equals 2. There we go. There's our first answer. And the rest are going to come very quickly now. What's the second row say as an equation?
Y minus 1/2 z equals 0.
Y minus 1/2 z equals 0. So now we know z. Y minus 1/2 z equals 0. What's a half of 2? 1. So what's y? 1. And now we can go all the way back to the first row, which we never changed from the very beginning. That was the x minus 2y plus z equals negative 1. Right, so let's write that one down. And I'm going to fill it in as I go. X minus 2, what was y? 1. Plus z, so plus 2, equals negative 1. Okay, 2 times 1? Negative 2 plus 2? X equals negative 1. Okay, so I think on the test, most of the answers are going to come out, I think all of them for the 3 by 3 come out to nice numbers. So if you start getting crazy fractions, you probably made a mistake with addition or multiplication, which is very easy to do. But on this one, we didn't. Okay. Any questions on that? It takes a little bit of getting used to, but I think after you do like 2 or 3 of them, it starts to get a little more repetitive. Okay? Less thinking. Okay. All right, let's try this one. Now, there's a couple things you could do here before you even start to make life a little easier. Yeah?
You can factor into the second equation.
Yeah, you could rewrite the second equation. You could pretend this one never even existed and put x plus y plus 2z equals 5. I like to have smaller numbers. If you don't want to do that, you don't have to do it. But that does a couple things for me. It gives me options what I want to be row 1. Because there's an x, each x has a coefficient of 1. So I could let any row be row 1. What's a little different in row 1 or equation 1 than the last problem? There's already a 0 for y. Whether or not you can use that to your advantage, maybe, you might have to change that from being a 0. You might have to mess that up. Because really what we want to get is 0 in what column first? The first column, which is which letter? The x's. If you had a 0 in an x spot, that would be helpful. A 0 in the y spot right now, it's probably not going to really help. All right, so other than it might make arithmetic a little easier. So let's set up our matrix, and I think I would leave the equations in the order they're in. So we've got 1, 0, 1, 4, 1, 1, 2, 5. And just double check me, because if I make a mistake, it will mess everything up. 1, 6, 8, 4. Now you might say, oh wow, we already have a 1 here too, which is what we want. We might have to mess that up. Okay? Until we get zeros in these 2 spots, I don't care what's happening everywhere else. Okay? You might have to mess up other stuff. till you work your way left to right. Okay, so do we already have a 1 in the upper left? Okay, then we're ready to start. What could we multiply equation row 1 by, and then add it to row 2 to cancel out the x's? Yep, so negative 1 times the first, added to the second, and where are we going to put the answer? In the second. And what are we going to do to get rid of the x's in the third row? Same thing. Negative 1 times the first, added to the third, put the answer in the third. So now we have 6 multiplications and 6 additions. So we have 12 calculations we need to do. Row 1, we just copy. In terms of calculations, I don't count copying as a calculation. That's not really. All right. Now, what's 1 times negative 1? Plus 1? And 0 is going to make arithmetic easy. So 0 times negative 1 is going to stay the same. And then we add it to 1. We still get 1. 1 times negative 1? Plus 2? 1? 4 times negative 1? Plus 5? 1. A lot of ones. Now we do the same thing again. 1 times negative 1 plus 1. 0 times negative 1 plus 6. 1 times negative 1 plus 8. 4 times negative 1 plus 4. 0. Great, we got a 0 here, but that doesn't mean anything. We don't really care about that. Okay, what we care about is right there. And same bonus right there, we got a 1 already. So we don't have to play kind of any games where we try to get a 1 there. So now we can go right into the next step, which is to get a 0 there. Okay, so let's write that down. How would we get a 0 in row 3, column 2?
Multiply the second row by negative 6.
Okay, negative 6 times the second. What else?
And then
Add it to the third row. And what else?
substitute.
And put that in for the third. And that's all we're going to do with that step. Okay, I think the only time you really would do 2 things at the same time is that first step. Most other times you just do 1 step. So we got 1, 0, 1, 4, 0, 1, 1, 1. And now we have to go through the calculation. What's 0 times negative 6 plus 0? 1 times negative 6 plus 6? 1 times negative 6 plus 7? Oh, that's nice. And then 1 times negative 6 plus 0? Negative 6. So in this problem, what ended up happening is we already got a 1 where we wanted it, so we already know one of our answers. What's z? Negative 6. Now the next one, what's this say as an equation? Y plus z equals 1. So we get y minus 6 equals 1. What's y? 7. So now we got y. And now we work back to get x. And what's a little weird here is you don't need y to get x. This is kind of like the small, medium, large drink problem. You don't need one of them to get the other 2, where in the last problem we did. So x plus z equals 4. X, what was z? Minus 6. So what's x? 10. So if things work out with a matrix, it's actually very efficient. So this problem, I think, worked out a little nicer than the last one. Okay. Any questions on that one? All right. So we got that one. Okay, so I'm going to come back and do the other problem in a second. But so far, all the problems we've done have had one solution. You get an x, a y, and a z value. It is possible that you end up with infinite solutions or no solution. Okay. Just to show you, let's see if I can make up a 2 by 2 matrix that would have infinite solutions. Okay. Somebody give me 3 numbers for the first row. 5, 3, and 7. Okay. And let's do 10, 6, 14. So now, how could you, forget about getting a 1 here, but just pretend you wanted to get a 0 here. What could you multiply row 1 by? -2, and then add it to row 2. What would happen to row 2 if you multiplied everything in row 1 by -2 and added it to row 2? And what would you get in it, though? Okay, you get 0, 0, 0, and this would be 5, 3, 7. Okay. What that means is if you get a row of zeros, that row no longer matters. So this is basically saying 5x plus 3y equals 7. And how many solutions are there to that? Well, one solution would be if you let x be 0 and let y be 7/3. That would be one. Or you could let y be 0 and let x be 7/5. There's another one. There's only 2 I can do easily in my head. What shape is this if you draw it? It's a line, right? You could put that in y equals mx plus b form. And how many points are on a line? Infinite. So there's an infinite amount of solutions to this problem. It might have been easier if the numbers worked out like this. Say it was x plus y equals 10. Then you're just trying to find 2 numbers that add to 10. Okay, hopefully if you saw that one, you'd say, oh, well, yeah, there's infinitely many numbers that add up to 10. Well, there's infinitely many numbers that work here too. All right, so that would be an example of a no solution, infinite solution. What do you think would happen with a no solution? What would happen to one of your rows?
If it was 5, 3, and then
Well, the first row you could keep the same, but something different would happen in the second
8.
row.
Like if the second row was like 5, 3, and the first row was 5, 3, 7.
Oh, okay. So change. All right. So like 5, 3, 8, and 5, 3, 7. So what would happen here if you did -1 times the first row and added it to the second? What would you get? 0, 0, 1. Okay, that's a problem. Because now you're saying 0 times something plus 0 times something equals 1. Nope, it doesn't. So that would be a no solution. Okay. So we don't really get into looking at problems like that too much. Okay. Most of them are going to come out exactly one solution. Okay, so with the time, we've got about still 20 minutes, so try that one. Okay, try it on your own and see if you can solve it. I think the solutions come out nice. If you get stuck, let me know. And I'll try to come help you. Okay, so let's look at this one. For this one, I think there's multiple ways you could kind of go about doing it. But I'm noticing that last equation already has a 0 in the x spot. That's useful. Okay, that's something I can take advantage of. Plus, I already have a 1 in the x spot in row 2. So that's something else I can take advantage of. So what I'm going to do is I'm going to leave row 3 where it is, but I'm going to swap rows 1 and 2. Anybody else do that to start?
Yeah.
Okay. So to write a swap, we're going to write it like this. Put an arrow, and we'll just say take row 1, take row 2, and we're going to store them in each other. We're going to swap them. So that's going to give me 1, 3, -1, -3. Let me get rid of this line because that looks confusing. Next row is going to be, let's see, 2, 1, 0, 0.
Isn't it negative one? Minus one?
Yes, thank you. And then 0, 3, 1, 8. Okay so far? All right. Now, I'm going to get a 0 here. Okay, how would I do that? Negative 2 times the first, added to the second, store the answer in the second. Good. All right, so let's do that. So we have 1, 3, negative 1, negative 3. 1 times negative 2 gives me negative 2 plus 2 is 0. 3 times negative 2 is negative 6, minus 1 is negative 7. Negative 1 times negative 2 is 2, plus 0 is 2. Negative 3 times negative 2 is 6, plus 0. Okay on that row. Any questions on that? Okay. Keep the third row the same. 0, 3, 1, 8. Now, what's the next step? What do you want to do now? Do what? We got to get this negative 7 to be a 1. You could multiply everything by negative 1/7. Now you're going to have really messy numbers to work with. Or you can get the negative 7 closer to a 1 by adding 2 times row 3 to row 2. Okay? It doesn't get it to be a 1, but it gets it to be a negative 1. And then we can easily fix it to be a positive 1. So I'm going to do 2 times the third row, added to the second row, and I'm going to put the answer in the second row. So, bless you. First row stays the same. Third row stays the same. 1, 3, negative. I think I drew my line through it on accident, but thank you. That would have been confusing. Or maybe I didn't even put the 1. Now we're going to double everything in row 3 and add it to row 2. 0 times 2 plus 0. 3 times 2? 6 minus 7. That's pretty good. 1 times 2 plus 2. 4. 8 times 2? 16 plus 6. 24. Now, how could I get a 1 in row 2? Yeah, just multiply everything by negative 1.
Yeah, Mr. Hager.
Yep.
16 plus 6 is 22.
Who told me 24?
Yeah.
Oh,
So what it was.
it's okay. I was concentrating more on trying to fit the number in the spot. 22. Thank you. But that's good. That's what usually happens when you do matrices. You make a small mistake, but hopefully you catch it. So now negative 1 times row 2. Put the answer in row 2. Basically change the sign of everything in row 2. That's it. Okay, so 1, 3, negative 1, negative 3. 0, 1, negative 4, negative 22. 0, 3, 1, 8. Okay, I'm going to put it here. What would we do now to get a 0 where the 3 is?
Multiply the second one by -3.
Negative 3 times the second
Plus the third
plus the third,
to the third.
and store it in the third. Okay, so rows 1 and 2, you're just going to keep copying them down. They're never going to change again. 1, 3, negative 1, negative 3. 0, 1, negative 4, negative 22. 0, 0. What's negative 4 times negative 3? 12 plus 1? 13. Negative 22 times negative 3 is 66 plus 8. 74. And I'm not sure we're going to get a nice answer here. We'll see. So the last row, we can get a 1 there, or we can basically just say this. 13z equals 74. Okay, any questions on that? And now, what would we do from here?
Divide both sides by
Yeah, we just divide both sides by 13, but I don't think 13 goes into 74 evenly, which doesn't mean we did something wrong. It could be the answer. Okay? I could check the answer very quickly. Let me plug it in and check it very quickly. So I've got 3 by 3 matrix. I've got 1, 3, come on, -1, 2, -1, 0, and I've got 0, 3, 1. 0, 3, 1. Okay, that's the left half. Quit, I need to plug in the right half, which is in a different matrix, 3 by 1, -3, 0, come on, 8. There we go. All right, so we're going to take matrix A, we're going to do that, matrix B, and the last answer is supposed to be 5.69. Is that what 74 divided by 13 is?
Yeah.
Yep, okay, so no, we did it right. It's just not a nice answer. And the rest of it, we'd have to plug back in using substitution to get Y and then get Z. On the test, I don't think I did one that comes out to fractions, okay? But if you understood what we did there, we did the process correctly. Okay? All right, so homework. Just double check. Okay, so 553. 1 through 6 is just describing an operation. So it's like, what would you add to row 2 to cancel out what's in row 3? So it's not actually doing a problem. So don't think that that's 6 problems. Okay. 17 is a 2 by 2 system. 18 is a 2 by 2. And I'm going to take off number 32. Okay, so you really only have 3 of the long ones. Yes. Okay, if you need any help, I will be after school today.